Okay, I'm going to describe some actually complicated physics with basic algebra here. And, just bear with me. I'm not going to do all the algebra because it will take forever. So I'm just going to do a lot of manipulations in my mind. Okay, I'm going to start out with de Broglie's wave equation, uh, which he proved, and many experiments verified it. The wavelength of de Broglie's wave equation around the different orbitals of an atom is lambda equals h over p. Okay, in physical terms, that would be equivalent to h over mv, which is the momentum. Okay, through many experimentations. Okay, keep that in mind. And then you have to keep in mind that Niels Bohr came up with the equation n lambda equals 2 pi r. And this was proved with science. It actually matched up through experiments. Okay. Now I'm going to substitute for lambda. I'm going to put this in here. So I'm going to have this n times this lambda, which is just going to be h over mv equals 2 pi r. Okay, and now I want to solve for, now linear momentum, P equals mv. Angular momentum can be written as the analog, which is the inertia times omega. Okay, so what I want to do now is I want to say that, from definition, okay, if you start at S over R equals theta, talk about a circle. Separate variables, you get S equals theta times R. Okay, so ds dt, derivative of the tangential distance with respect to time, equals d theta dt times R. ds dt is the tangential velocity, v, and d theta dt equals omega, and that's times r. And I can also prove that the tangential acceleration equals alpha times r. So here we're going to, the first thing I want to do is say force times the perpendicular distance from the axis of rotation to the line of action of the force. If the force is actually perpendicular to the line of action of the force, then torque Fr also equals inertia times angular acceleration. That's like saying force times force equals mass times acceleration, but the circular version of it. Okay. Now here I want to replace this force with an ma, mass times acceleration equals force, and this r stays here. And I have I here, and then I have for the alpha, I have v over r. Okay. A over r, because alpha is going to be a over r. I'm sorry. A over r. Okay. Now, if I multiply both sides by r, I'm going to have I, just for a point mass, equals m r squared. Okay. So now, also, I noticed that omega here, omega would be v over r, divide both sides by r. So I have this angular momentum. I was calling it linear momentum in my other video. That's the reason I took it down. It's not linear momentum. It's angular momentum. Angular momentum equals inertia times the angular velocity. Okay, so inertia, I found, is mr squared. And alpha is going to be a over r. Omega is going to be v over r. Sorry, v over r. Okay, so the angular momentum is just going to be, well, r is going to go itself once, r is going to go at r squared, r times. So this is going to be mvr. That is the angular momentum. Okay, so I'm getting up to Niles Bohr. Don't worry, I'm getting up to that, building up to that. Okay, now that we have that, we also know that from this equation here, we have nh over mv equals 2 pi r. Now I see this VR here. I want to try to replace that VR by this equation, something I can do with this equation. Okay, so if I multiply both sides by v and divide by 2 pi, I'm going to have VR will equal to mass, VR will equal to nh over nh over 2 pi m. Oh, that's perfect. VR equals nh over 2 pi m, like that. And I plug it back in here. So now I have L equals mvr. Well, VR is nh over 2 pi m. So I'm going to plug it in. I'm going to m nh over 2 pi m. Okay, this is like trying to clarify a whole bunch of physics for you here. Okay, so now then the angular momentum, L is angular momentum, can be expressed using de Broglie's method. nh over 2 pi. nh over 2 pi. Okay. Wow. That's pretty good. Okay. And I will be using that. Okay, so now I wanted to show you how that's derived. Okay, now, so in general, we have this angular momentum for n orbitals is going to be equal to nh over 2 pi, like that. All right. Now, the force between two charges is given by k q1 q2 divided by r squared, where k is a constant. But we're talking about electrons in different orbital levels. So we would have 2 electrons here. So the force is going to end up being equal to k e squared over r squared. And you're also going to have a centripetal force, which is trying to pull that electron in toward the center because it's going around in a circle. And that's going to equal to mv squared over r. All right, so I can set the two equal to each other. That's the nice thing. I can set the two equal to each other. So now I have k e squared over r squared equal to mv squared over r. And let's generalize it. Give it an n there and give it an n there. Okay, now from our linear momentum equation, I said it again. It's angular momentum equation. From our angular momentum equation, we have mv sub n times r sub n in general equals nh over 2 pi. So here what I want to do is I want to solve for this v. Okay. And when I solve for the v, that's really just dividing through by mr sub n. So I get the v sub n is going to end up equaling to nh, still have that, divided by 2 pi rm. 2 pi r sub n m. Okay. And that looks pretty good. So now I'm going to substitute this here in for this v here. Okay. And when I do that, I'm going to I'm going to do a little manipulation here. I'm going to substitute this ke squared over r sub n squared, like that, equal to m times this nh over 2 pi rm. I'm going to square that like that. And I'm still going to have my r sub n. This is going to be r sub n. Okay. A little manipulation. I can see something very interesting here. These r squareds are going to cancel when I square this, because this is like in a denominator here. So if I flip it over, it's going to become a numerator. I square it. Okay, when I multiply both sides and do all the messy algebra, I'm just going to go through it real quickly for you. Yeah, you can do the messy stuff if you want to by squaring everything and doing it. But anyway, trust me, this will cancel with this. And I will end up with ke squared, ke squared times r sub n equals h squared over this messy stuff, 4 pi squared, mke squared, all that stuff, and it'll be multiplied by n squared. Okay, now then I do a little more manipulation, and I end up getting I jumped ahead. Yeah, okay. So now I'm still going to have this m up here. So this m squared is just going to, m goes in itself once. Oh, because m will be up here. And that's going to be m squared. So m squared down here. Yeah. And then m goes into itself once. M goes into m squared, m times. Okay. And now I'm going to go ahead and divide through by this to get r sub n by itself. So I can end up with r sub n equals h squared over 4 pi squared mke squared, all that multiplied by the number for the orbital squared. Okay, and this will tell you the radii of each time the electron jumps to a different energy level. Sorry about the drawing. Okay, so this would be the R1. Then you might have R2, and so on. Okay, so that's basically what that means. Now, what Bohr did is he said, well, that's Planck's constant. Pi is a constant. The mass of an electron is a constant. K is a constant, and E squared is a constant. All these are constants. So he did all the math, and he come up with this. R equal to 5.29 times 10 to the minus 11 meters times n squared. N being the orbitals. And that's really ingenious because he could find the different orbitals for, the Bohr's electron orbits. He could find the different orbits, okay? Different radii for the different orbits. And then the hydrogen atom, okay? So I think that's really interesting. And at the ground state, what is the radius at the ground state? The ground state radius would just be this 5, don't even need parentheses because n squared is going to be 1 squared. It's just going to be that 5.29 times 10 to the minus 11 meters. Okay? So if you're like me and you're taking physics and you're like me, you want to know where everything came from. Okay? When you see these formulas. Okay, and this looks like a simple formula, and you can just memorize this if you're taking physics to find the nth orbital. I'm sorry, to find the nth orbital, that would be orbit 1. But to find the nth orbital, use this formula. And like if you wanted to find the second orbital, would just be 5.29 times 10 to the minus 11 meters multiplied by n squared. For the second orbital, that'd just be 4. So you just multiply by 4. And that would give you the second orbital, the radius of the second orbital. So that's basically what I was doing here, is just kind of showing everybody, that how you can actually start out with something simple and use reasoning to derive something very complicated. And Niels Bohr didn't have the equipment like we have now. But experiment after experiment with our spectrometer, mass spectrometer, has proved over and over again that this formula is correct. So finding the different radii for the hydrogen atom, different energy levels. Okay, and I think that's really bizarre that he was able to do that just using basic algebra, manipulations. So that's what he had to go through. And I did all of this because I wanted to show each person, I wanted to show each step, so any person who wants to view this video can see each step that leads up to Bohr's derivation of the electron orbits with specified radii. Okay, so this is the generalized formula for specified radii in the hydrogen atom. It's called Bohr's orbits. Okay, that's how he derived that formula. Okay, thank you for watching.